This video is a 1-hour presentation of the USGS Evening Public Lecture Series titled Post-Fire Debris Flow Early Warning, the Case for Forecast-Based Warning Systems. The presentation is being hosted in the USGS Menlo Park facility. The host welcomes the audience and introduces the speaker, Dennis Staley, who is a USGS research scientist. As Dennis is giving his presentation, he is continually pointing to and referring to slides presented on the screen. The slides are a mixture of charts, graphs, and photos. At the end of the presentation, there is a question and answer session with members of the audience.
Hello. It is always a delight to see so many familiar faces. Thank you for coming month after month to the U.S. Geological Survey continuing monthly public lecture series here in Menlo Park. And my name is Leslie Gordon, and it is always my pleasure, or not always, usually, frequently, my pleasure to introduce the speakers. Before I introduce tonight's speaker, I do this all the time. I want to let you know about next month's lecture because I want you to come back. Next month, Barbara Koos, K-U-S, who's a biologist with the USGS, is a specialist in endangered species and birds. She's going to be coming and talking about endangered birds on November 29th. That's the week after Thanksgiving, if you're worried. So please do join us next month to hear about endangered birds. Endangered birds aren't funny. Turkeys. Yeah, we're going to eat them all the previous week. That was okay. I'm just kidding. I like to have fun with you guys. This is good. It is my pleasure tonight to introduce our speaker, Dennis Staley. Dennis is a research scientist with the USGS Landslide Hazards Program. He usually resides in Golden, California, so we're delighted that he made it out here to speak to us. And although he is in Golden, he is an expert on especially debris flows following wildfire in California. And if you've lived in California for a long time, you know this is a pretty typical pattern. We have wildfires. It gets really hot and dry in the summer and fall. And then starting in January-ish, we get a lot of rain. And we get a lot of horrible, deadly debris flows following that. So it is my pleasure to introduce Dennis Staley, who will be talking about post-fire debris flow early warning and the case for forecast-based early warning systems. Please welcome Dennis Staley.
Thank you very much. It's really a privilege to be here tonight. It's my first, I've been at the USGS since 2007, but it's my first trip to the Menlo Park campus, and it's been fun so far, and I'm happy to be here. So thank you very much for the invitation. The impetus for my talk tonight is after the Montecito event, the debris flows that happened earlier in January in Southern California. There's been a lot of talk about how we can better protect the public from these types of hazards. And there's been folks out there that have floated the idea of developing sort of a community-based early warning system where they're established monitoring network up in the hills above town to monitor for flow, if there's flow in the channels or intense rain up above the population. But there's some complicating factors. So while these ideas are very well intentioned, there's some things that people need to think about, and things about post-fire debris flows that are different than other types of landslides that make monitoring for early warning a distinct challenge. So I'm going to be going through and kind of talking about post-fire debris flows and thinking about early warning systems and what those mean, and then some of the challenges that we face specifically dealing with post-fire debris flows in the context of early warning. So the talk focuses on post-fire debris flows. Other types of landslides, there are more appropriate ways of doing early warning that does involve much more reliance upon monitoring itself. So they turned off the lights, so in case you guys end up taking a nap, there's 4 key points that I really want to hammer home tonight. The first being that post-fire debris flows occur within minutes of intense rain and happen repeatedly after fire, even in the same watershed. The second is that early warning systems involve much more than just monitoring or detection of flow or intense rainfall. If you are measuring intense rainfall or flow in the watershed up above a susceptible population, it's likely too late to take any meaningful action. And then finally, the only 100% effective form of risk mitigation is awareness and avoidance. So getting out of the way of these types of events is the only successful way, 100%, to reduce risk to the public. So I'm going to start off giving a brief overview of what post-fire debris flows look like, what they are, how they happen, and how they compare and contrast to debris flows that are initiated from other types of geomorphic processes. So a fire imprints a pretty significant footprint on the landscape. Some pretty dramatic changes that occur. Some that you can see and some that you can't see. So those are sort of the 2 loose groups of categories of changes that I'll talk about. So the ones you can see include the total combustion of the canopy. So the fire rolls through, burns up all the vegetation, the actual trees and shrubs, but as well as the protective litter and duff right at the surface on top of the soil. And what this does is it makes the soil more vulnerable to erosion processes from gravitational forces, rain splash detachment, overland flow, rill and gully erosion, channel erosion, all the different types of things associated with both water and gravity, and wind too, but that's not so much the focus of this talk. The second set of changes that occur are changes that occur within the soil itself, or physical and chemical changes within the soil column. And here, what happens is that the fire actually alters the way that the soil can absorb water during a rainfall event. So relative to an unburned state, after a fire rolls through, it's oftentimes the case where the soil can't absorb moisture quite as rapidly. And so given the same amount of rainfall, you're going to have more runoff and more erosion in a burned area than you would relative to an unburned area. And these enhance runoff and erosion when you have a steep watershed combined with a downstream population. That makes them pretty vulnerable to hydrologic hazards following wildfire when you get sufficient rainfall. So if we look at a drainage basin that produced a post-fire debris flow, again, this is in the mountains just up above Montecito. There's a few distinct features that are evident and not evident in this type of event. So what you have is the fire burned through the landscape, consumed pretty much all of the vegetation. This is typically chaparral, so pretty densely vegetated. But that burns hot and it goes away. So the basin becomes pretty much moonscaped afterwards. And so there's no vegetation protecting the surface. When you get intense rain, that rain falls directly on the soil. The soil can't absorb that moisture quite as quickly. So it generates runoff. That runoff moves downslope, and it progressively picks up more and more material in the downslope direction. So you may start up high, and you just have some kind of clear water running down, and then it picks up more material in the form of in the rill network, and then finally starts scouring out the gullies and the channels, and picks up more and more material, and eventually becomes a debris flow. One thing that's notably absent in many watersheds burned watersheds that produce debris flows are shallow landslides. So you don't see evidence of many discrete failures. I'd say 90-something% of the debris flows that we've documented over the past 15 years, 20 years, have really been generated from runoff alone, and not too much evidence of shallow landsliding. So for those of you in the Bay Area, you're much more familiar with debris flows that are generated from shallow landsliding processes. So what will happen here is you will have a discrete failure, typically in an area of flow convergence, both surface and subsurface. As you have rain fall down, the volume of water within the soil column itself increases during that storm, during prolonged rainfall. And at some point, some critical threshold is reached where the surface can't stay in place anymore. There's too much water, it exceeds the strength of the material, and that material then fails, runs downslope as a debris flow, and then ultimately could potentially impact infrastructure or communities at the base of the slope. In this case, this is a pretty famous event from 1982 in Pacifica, California. where after a period of pretty prolonged rainfall, there was this event that unfortunately resulted in 3 fatalities in this home. So there's clear differences between sort of the initiating mechanisms of debris flows that are generated from landslides versus those that we see in burned areas that are generated from runoff. So just to hit this point one more time, if we compare a burned and an unburned landscape, we've got our unburned area. It's a clear cut in eastern or western Oregon. On the left-hand side, you have your discrete failure of material, so you can clearly define where the stuff came from that made a debris flow. And then if you compare that to the burned area on the right-hand side, there's a notable absence of that discrete source of material. So instead, you have these sort of striped features as you move down in through the watershed, which is where you start entraining material in the form of rill erosion and then scouring out the gullies, the channels, and then ultimately there's some kind of transition to debris flow further down. So there's a clear difference in the initiating mechanisms, which means that the tools that we use for forecasting debris flows and predicting where they are going to happen and how big they're going to be have to be different for post-fire debris flows that are generated from runoff versus those that we use from landslides. So what we do is we've now established over the past 15 years a pretty substantial protocol for going out after a burn and doing some field work and establishing a monitoring network so that we can learn more about how post-fire debris flows initiate and how they get bigger. It's kind of we take a look at it and see for a burn area, there may be some unique physiographic characteristic or lithologic characteristic that we want to say, hey, we want to see what that effect that has on debris flow generation or erosion processes. And then we'll opportunistically select some watersheds that we think probably would produce debris flows, and we'll go out and we'll put out a bunch of equipment in the field. So I'm going to be talking quite a bit about this little watershed here over the next few slides. This little watershed is located about 20 miles east of Pasadena at the front of the San Gabriel Mountains, just above Duarte. It's pretty small. It's maybe 5 football fields long by 3 football fields wide. And within this watershed, we have 2 different monitoring locations. We've got a hill slope monitoring location where we're looking at properties of rainfall as well as soil erosion. And then further down in the watershed here, this little blue dot, we're measuring channel flow and rainfall there as well. And we also set up a video camera. So hopefully the storm will happen during the day and we can take some videos and see what these things look like. And you can learn a lot just by looking at the video evidence of what happened during a debris flow event. So this is what the view from the camera looks like. It's not the big dramatic, landscape photo, but it can get some pretty good footage. So we have a couple engineers here for scale. So the channel is maybe 2 meters deep by, 3 or 4 meters wide or so. So not a huge channel. Again, this is a really small watershed, a few football fields wide by 5 football fields long. And it was very steep though, so the average gradient's over 30 degrees, so very, very steep. And fortunately, just below this basin is what's known as a sediment retention basin. So it's basically a bucket that LA County Department of Public Works will put out that's huge and it'll catch material so it doesn't spill out into the neighborhood. At least that's the theory behind it. Hopefully they don't fill up. So we were fortunate enough to get a debris flow caught on camera, and it happened during the day. So that's great. So usually they happen at night, and we're not able to quite get the video footage. But we got this one during the day. So this is on January 20th of 2017. The fire was in September of 2016. I think this was probably the 3rd or 4th rainstorm. There had been a debris flow previous to this in this watershed in December. And hopefully the video will work. So you can see there's just kind of some flow in the channel, but nothing that's spilling over. And all of a sudden there's a big surge. Lots of mud, rocks, sticks, but the flow is pretty dynamic. And if you look real closely, you'll start seeing some fairly good-sized clasts in there. So good-sized rocks that are moving through. You definitely wouldn't want to be standing where our engineers were standing in the earlier image. The flow keeps increasing. At this point, the rainfall intensity is probably around 30 millimeters an hour, so not very super intense. And the flow keeps kind of comes and goes in stages. It gets worse for a second and then just kind of settles down a little bit. And then I'll just kind of let the rest of the video speak for itself. So all of a sudden, you get the Indiana Jones boulders. Now, you think about the impact that would have on any infrastructure downstream or any bridges or culverts or anything like that. So clearly, these are pretty hazardous events. And again, this is a really small watershed. This is a few orders of magnitude smaller than those that were up above Montecito. So you can imagine with even more rainfall, lots more intensity of a much higher intensity rainstorm, it could be considerably problematic for folks living downstream. If we have time at the end, I'll show it again. Yeah, I'm gonna try to keep it. Oh, maybe I will show it again. So we also have our rainfall data and flow data that we recorded at this exact same site. So I'm going to walk you through the graphs real quick. They're not too terribly complicated. We have on both, we've got rainfall up above and flow measurements here in the lower graph. We've got time on our x-axis from 7:45 to 9:45 p.m. UTC on the 20th of January. For the rainfall graph, we've got 15-minute rainfall intensity here on the y-axis on the left-hand side, and that corresponds with this blue line. And we've got our total storm accumulation here on the right axis, the y-axis on the right-hand side, and that's our black line. You can see that not much in terms of total storm accumulation, so maybe 42 millimeters or so not quite 2 inches of rain. And then our 15-minute intensities peaked at just over 30 millimeters an hour, which is about the equivalent of a 1 to 2 year recurrence interval rainstorm. So not a very significant rain event. Based on the video evidence, we saw that with the debris flow, the main surge started at 8:42 p.m. And if we look at our intense rainfall, the onset of that was at 8:38 p.m. So we have 4 minutes between it raining hard and there being a debris flow. The lag time's even shorter, just looking at the flow here. So we had our onset of flow. So when we went from just kind of a trickle in the channel to some more dynamic flow coming down at 8:41 p.m., and then the main part of the debris flow came down at 8:42 p.m. So 1 minute between measuring detectable flow and the flow itself, the big part of the flow starting. That could be the real hazardous portion. So these things happen really fast. They don't take much rain. They don't take a very long duration storm. These things can happen in the first few minutes of it starting to rain in the very first storm after fire. And it can continue, the hazard can continue for a period of years following wildfire. So debris flows, not only do they happen fast, they can happen repeatedly in the same watershed. So you may go through a storm and there's no debris flow in that particular location, but it might not have rained hard enough. So that doesn't mean you're out of the woods for the rest of the year. Also, you may have experienced a debris flow in that watershed, but that doesn't mean it won't happen again throughout the season. This picture shows Mullally Canyon. It was in 2010 after the 2009 station fire. This watershed produced debris flows in December, January, and again in early February, and in the same storm, 3 different distinct episodes of debris flow, the second of which filled up the sediment retention basin and then spilled over into the neighborhood. So surges 2 and 3 were the ones that caused the problem, and this is one of the 40-something homes that were damaged during that event in La Cañada, which is just east of Pasadena. So they happen quickly, they can happen repeatedly, and then bang for the buck, they're worse than flash floods. So all things being equal, if you dump the exact same amount of rainfall and produce a flood, or you in the exact same amount of rainfall and you produce a debris flow, the debris flow is going to be worse for a couple reasons. First, the height of the debris flow itself, or the peak stage of that flow, can be up to 5 times greater for a debris flow relative to a flood with the exact same amount of moisture input. The reason for that being all the rocks and sticks and material that's in that flow. So you have a higher peak stage. Also, the velocity can be about the same or greater for a debris flow relative to a flash flood. The reason it's hard to kind of put a number on that is because the debris flows have a very intricate dynamic in terms of the velocity profile. So there's a profile of velocities both vertically within the flow, but also temporally. They speed up, they slow down. Certain parts are moving faster than others. So getting a true measure of debris flow velocity is a real challenge. It's not like measuring clear water flow. But the take home here is that your flow can be bulked to 5 times the height, and it's moving at least as fast as the flow. And then you have all those big boulders and rocks and sticks and mud, and that it just increases the impact forces associated with the flow itself. And so the destructive potential of a debris flow is much higher than that of a flash flood. And that's not to discount how hazardous a flash flood can be, because those can be pretty hazardous as well. But all things being equal, the debris flows are worse than the flash floods. So we've learned sort of about the physical characteristics of the event, but why do we need early warning? Well, this is a picture, a map showing burn areas from 2000 to 2017 in the United States. Now, not all of these areas are steep enough to produce debris flows. Not all of them are populated enough for there to be sufficient risk to really pay too much attention. But if we could just look at 2018 itself, there's 8.1 million acres that's burned this year. Now, that's a huge number. I don't really have any context for that. So it's equivalent to 12,600 square miles, 32,700 square kilometers, or for better idea of getting some context, that's 10.3 Rhode Islands. And that's just in 2018 so far. We're still in the main season in Southern California, and we know that place can produce some pretty good firestorms every 5-6 years or so. So there's a pretty tremendous amount of population that could potentially be at risk to post-fire debris flow hazards. And as the population increases, as we expand into the mountains, as we build on alluvial fans, that hazard is just going to keep increasing over the foreseeable future. And these are places maybe last year they really weren't even thinking about debris flows. Since fire is puts such a transient input on the landscape itself, you may not be thinking about this. All of a sudden there's a fire and you've got to start thinking about debris flows where there may not have been a problem for 50 years because there weren't any fires above you. So if we were to summarize the key points of sort of the sciencey stuff that we just went through, we've identified that post-fire debris flows originate differently than than debris flows that come from other types of landslides. Post-fire debris flows can be triggered after only minutes of intense rain. They can occur repeatedly after fire in the same watershed, and they're more destructive than flash floods. So if we add all of those things together, we need to have a specific early warning system to post-fire debris flows in order to reduce public risk to these types of hazards. So we're going to talk now about what early warning systems are, how they're defined, the different components of them. And fortunately, the United Nations Office for Disaster Risk Reduction has already put together a nice handy definition for us. And I will read this one. So it's an integrated system of hazard monitoring, forecasting and prediction, disaster risk assessment, communication and preparedness activities, systems, and processes that enable individuals, communities, governments, businesses, and others to take timely action to reduce disaster risks in advance of hazardous events. So that's a mouthful, but there's some pretty important components of that. First, there's sort of the technical infrastructure of the warning system itself, the pieces that actually make a warning system. And then finally, there's this concept of timely action in advance of hazardous events. And we're going to explore both of these in a little bit more detail. So how do we currently provide early warning for post-fire debris flows in the western United States? Back in 2005, the USGS partnered with the National Weather Service to implement a post-fire and flash flood and debris flow early warning system in Southern California. This included the San Diego Forecasting Office and the Los Angeles Forecasting Office. The relationship between fire and floods and debris flows is pretty well established down there. The public is pretty aware. So this is a good test bed for coming up with a way that we can actually do early warning for these types of events. Since 2005, the warning system has been pretty successful in Southern California, And there's a significant degree of interest in expanding this to other locations in the western U.S. So we're currently in the process of working with the Weather Service to get these warning systems going. And right now we're working with your forecasting office, Monterey, looking at some of the fires that burned this year and last. Sacramento, Reno, other places throughout the West that have had some pretty significant fires and have debris flow hazard. We're slowly expanding the warning system to those locations. So if we think about, we'll look at each one of the three components. The first being the monitoring, forecasting, and prediction. This is where the rubber meets the road in terms of when do we actually have debris flows during storms, so that we can look at the forecasts, we can look at the observed rainfall rates and make some predictions as to when we're going to have our debris flows. The USGS provides what we call rainfall intensity duration thresholds. And this is pretty simple. They're just the rainfall rates above which you need to be concerned that debris flows will be initiated. So another graph, but this one's pretty simple. We have our duration over which we're measuring rainfall intensity here on the x-axis, and then our actual intensity value here on the y-axis. We've got two different color-coded items on the graph. The little blue X's represent the rainfall intensities that are associated with storms that did not produce debris flows. The little red circles are the rainfall intensities that are associated with storms that did produce debris flows. And you can see there's a bit of separation between those two. And so we can define a rainfall threshold in a variety of ways, each of which has its own compromise. You can draw that line or define that threshold at the upper limit of those blue X's or those rainfall intensities that did not produce debris flow. Now the compromise here is that you're under warning. So you're going to have some debris flow producing rainfall below your threshold. So there's some consequence there because you're under warning the public, and there could be a debris flow that's generated, and they're not aware that that's even a possibility when you're under the rainfall threshold. Another option is to define it at the lower limit of those debris flow producing intensities. But again, the compromise here is that you run the risk of overwarning, of having too many false alarms because you're saying, hey, we could have debris flows, and then nothing happens. You can see quite a bit of blue X's here above that line. And then finally, you can develop some objective function where you're weighting and trying to balance the false and failed alarm rates. And there's a variety of ways of doing that, but that's probably beyond the scope of this talk. But the idea here is you want to identify those rainfall rates that could be problematic. And the USGS does this, and then we provide that information to the National Weather Service. If we think about the storm that we had the video for and put that in the context of a rainfall threshold, here's our rainfall threshold that's been defined for that area. Just under 19 millimeters an hour is the 15-minute threshold intensity. Again, the rainfall intensity is the blue line here. We can see that we exceed our threshold at 8:38 p.m. and had our debris flow at 8:42 p.m. So 4 minutes of lag time between when the flag would be raised, the hey, we have problems here, and the actual debris flow happening. So not much time. Once we've defined these thresholds, we pass that information off to the Weather Service so that they can put it into their software that they use for forecasting, the modeling that they do to figure out how hard it's going to rain and when that rain will happen, as well as their observations of rain in real time from rain gauges and radar. They have the technical infrastructure to be able to pull this off. They're a 24/7 shop that can ingest lots and lots of real-time data at one time. So they're clearly the right choice for making these decisions and keeping an eye on the rainfall rates for when we need to be concerned about debris flow generation. So this is just the Los Angeles forecasting area, and they can put in all of the different burn areas that they're concerned with, and then compare the forecasted rates and the observed rates to our threshold, and then issue their various warning products. And my computer seems to be hanging. There we go. So the second component of the infrastructure of that warning system is disaster risk assessment. It's probably a good time to talk just real quickly about the difference between hazard and risk. Hazard is just the likelihood that that event will happen. So you could be in a mountainous watershed. It can have a very high debris flow hazard. It can produce debris flows very quickly when it doesn't take much rain. But if there's no people there, there's not much risk. So risk really concerns itself with the impact that that event would have on the downstream population. So again, if you don't have any population, there's really no risk. You may have an extreme level of hazard, but not necessarily any risk. Now, the science of actually predicting and defining areas of risk is largely in its infancy for landslides and debris flows. It's hard to make those calculations as to where the flow is going to go and how fast it's going to be going. So at the USGS right now, we're still working in the context of hazard. And we put out maps after each significant wildfire that shows how likely a debris flow would be given a certain amount of rain and how big that flow would be should one occur. And in this case, this is Montecito down here. And these are the watersheds up above Montecito. And what we're illustrating is the likelihood of a debris flow in response to a storm that has a peak 15-minute rainfall intensity of 24 millimeters an hour. So a little under a quarter inch of rain in 15 minutes is what the design storm is here. And you can see that these watersheds are in red, so we're going to assume that's bad, and in fact that is. That's in the 60 to 80% chance of producing a debris flow in response to those rainfall intensities. So the USGS identifies the hazard, and then we partner with a couple different federal agencies as well as some state agencies who go out after the fire and within 7 to 10 days typically put a report together that identifies specifically the places at risk. So they'll identify if there's a school in the floodplain, the infrastructure that may be at risk for debris flow. But we really have to rely upon, at this point, we still have to do this in the field, and so we rely upon our federal partners in the Forest Service and other Department of Interior agencies, as well as some of the state geological surveys in California, Arizona, Oregon, Washington, and now Utah and New Mexico, and a few other states. So between the three of us, we can identify both the hazard and the risk associated with that hazard. And then finally, the third piece of the puzzle is the communication and preparedness activities, systems, and processes. Now, this is where the Weather Service truly is rock stars. They have the system in place to be able to communicate with the public quickly, efficiently, and everybody's kind of familiar with their products already. We've all been watching TV and had the little thing go across the screen for a thunderstorm or a winter storm warning. So we're familiar with those products. And now with social media, it just makes it easier to get that information out to the public. They have 3 different categories of warning products that they can put out. The first being the weather outlooks, or the special weather statements, and partner notifications. These typically can go out anywhere from several days to a few days in advance of an event. So what will happen here is that they'll identify there's a significant storm that has a potential of impacting a burn area or a set of burn areas in a particular location. And they'll reach out to their partners through a series of webinars, or phone calls, conference calls, and online products that people can view and say, hey, we got a storm coming that we're concerned. In this case, this was on January 8th of 2018. This is the special weather statement that they put out in advance of the events in Montecito about a day beforehand, where they identified that there was an extreme risk of mud and debris flows for recently burned areas in Southern California. They had been doing these webinars prior to this one, so I think they started on the 5th, and the flow itself was on the 9th. The second group of products is that of a flash flood and debris flow watch. Now, in this case, you're looking at a day or so to a few hours in advance of an event, and they'll say, hey, there's a storm coming. It's got the dynamics that can produce intense rainfall, and it's going to impact burn areas in our forecasting region. But we're not quite sure the precise timing of that event, and we're not quite sure where that intense rainfall is going to actually occur. But this is sort of the actionable phase of any type of warning system. This is where you actually have time to get out of the way. So this is when the emergency management crews go into overtime, start notifying residents, letting people know that, hey, it might be time to get out because there's a storm approaching. And then finally, the warning occurs less than or equal to about 2 hours in advance of intense rainfall. In this case, we've got our band of really, really high rain rates approaching our star of Montecito. And at that point, the Weather Service would have issued a warning already because they'd been monitoring this band approaching over the past half hour or so. So getting back to our three components of the warning system itself, we can check the box next to monitoring, forecasting, and prediction. The USGS provides thresholds, and the National Weather Service implements those thresholds. Our disaster risk assessment, it's a combination of combining forces from the USGS, other federal agencies, and state agencies to let the community know where there could be problems. And then finally, we really rely upon the Weather Service, but we try to help them out as best we can with the communication and preparedness activities. So we can check all three of the boxes. We meet the definition, at least in terms of the technical infrastructure of a warning system. But there's a second part to this, and this is where the challenge really comes. So we want to enable individuals, communities, governments, businesses, and others to take timely action to reduce disaster risks in advance of hazardous events. So the two key parts of this are timely action and in advance. And we're going to walk through what happened in Montecito and in order to give sort of a case study of what a relatively successful warning approach looks like and how this might be implemented in real time. Setting the stage for the Montecito debris flows was the Thomas Fire that started in December of 2010. It's this little red area down here, a little east of Santa Barbara. It burned for about a month. It started just outside of Ojai and then spread north and then westward. And the rainstorm that actually produced the debris flows was what finally caused full containment of that fire. So the fire wasn't fully contained until the 11th or 12th of January. So it burned actively for over a month. Leading up to the event, the warning products were issued by the National Weather Service. Again, the debris flow was on January 9th, about 3:40 in the morning. So on the 6th of January, at 4:11, they issued one of their, maybe the first or one of the first special weather statements via Twitter, as well as all of their other ways of getting information out. On the 7th of January is when the flash flood watch officially went into effect. So we're almost 2 days in advance of the events. And then finally, the warning was issued at officially issued at 2:41 a.m. on the morning of January 9th. Now, it's important to note this time. It's early in the morning. And so that has consequences later on as we step through looking at what happened. It's a radar loop of the storm on January 9th. Montecito, this is the outline of the Thomas Fire here, the red polygon. The star is Montecito itself. For those of you who aren't familiar with this type of mapping, the red and yellow indicate bands of more intense rainfall. The green is less intense rainfall, and then if it's clear, that means the radar is not detecting any rain in that particular location. Oops. And so we'll go to the video here and take a look at what that looked like. We've got an intense band off to the west. We'll see this intense band start popping up here, move over Montecito, and then just rapidly dissipate. So this is a very short-lived event. It was probably 35, 45 minutes from when you first start seeing that really intense rainfall to the south and west, and to passing over the area and then completely dissipating and going to much lower intensity just off to the east. So it's a very short-lived event. Depending on which rain gauge you look at and how long over which you look at the intensity, it was anywhere between a 50-year recurrence interval and a 200-year recurrence interval rainstorm. So a pretty significant rain event.
How long did that last in real time again?
It was 30 to 45 minutes for that intense band to rain through. The storm itself kind of rained lightly for a few hours prior to this event and then lasted another few hours. And it was the first storm following the fire. The storm generated debris flows in several different watersheds. To the west, we have Cold Springs and Hot Springs Canyon that join to make Montecito Creek. Oak Creek's kind of a small guy. San Ysidro Creek is a bigger watershed and had quite a significant proportion of the damage. Buena Vista Creek and Romero Creek. We're going to focus largely on what happened in Montecito Creek and San Ysidro Creek. But the dots here on the map indicate houses that were damaged according to a survey done by the county. And you can see that the red dots, which indicate complete damage, and then orange and yellow are extreme and moderate damage, extend from the front of the mountains in the fan apex all the way down to the ocean. So something that impacted the community, the entire north-south extent of the community. The flows actually shut down the 101 for a period of several days. So really an impactful event to the community of Montecito, but as well as to neighboring communities because of the damage to the infrastructure. We were able to recreate the meteorological and seismologic characteristics of this event because of some fortunate placement of equipment that was already there, put in by the city. So if we look, we have a couple rain gauges. These are the blue dots in the area. We'll focus on the rain gauge in Montecito. We've got a seismic station both in Santa Barbara and one in between Montecito and Summerlin, right along Romero Creek. And then we have two locations where we were able to obtain precise timing of when the flow impacted that particular location. The first being homeowner footage from a security camera that was just at the very top of Cold Springs Canyon. We'll see if the video loads. So it's kind of raining. It's hard to tell how hard it's raining in a dark video, but it's raining, but there's no real evidence of anything going on in the immediate foreground or background. The rain seems to pick up, the camera shakes a little bit, and then all of a sudden, you get a wave of material. And that's how quickly the debris flow can roll through. You'll have no evidence of any flow, and then all of a sudden it's chaos and things are destroyed. So I think that was the last frame of footage from that security camera. There was also, in San Ysidro Creek, there was a gas explosion. So buried underneath the channel at this bridge location, a few meters deep, was a gas line. The channel scoured out. Some rocks probably caused a spark, which make the gas explode. And then there were several homes that were consumed by the inferno generated by the gas line.
That's a 38-inch line?
I'm sorry?
Was it a high-pressure 38-inch line?
I don't know the specifics on the line itself, unfortunately. But we were able to get the precise timing of that from 911 calls. People all of a sudden were woken up and they see a huge ball of fire, so the first thing they're going to do is call 911. So we were able to obtain the precise timing that rupture occurred. We're going to reconstruct the data from the rain gauge and the seismic station here. We're going to focus on, this is the graph on the top is the rainfall data. It's 5-minute intensity on the y-axis and time on the x-axis. We'll take a look closely at this orange line. That's the rain gauge in Montecito. So if we plot our threshold rainfall intensity here, the threshold at 5 minutes is somewhere just below 60 millimeters an hour. You can see we clearly exceeded that during the rainstorm. So the rainfall threshold was exceeded at 3:40 a.m. Our peak 5-minute intensity, so that's that 200-year recurrence interval rainfall intensity, was at 3:43 a.m. The gas line explosion, the first calls came in at 3:47 a.m. The security footage was at 3:49 a.m. Moving down to the spectrogram here, where we're looking at seismic data. My computer hung again. We've got what we're plotting here is the frequency of the signal, and then the colors indicate strength in that frequency. And so we're starting to see increased strength in the higher frequency signal here at about 3:43 a.m. And then finally, the one we're more familiar with, the seismogram on the bottom. My computer's really slow today. So we start seeing increases in the strength, the velocity of the seismic signal at 352. That's where we exceed sort of the ambient noise of the area, and we can say, hey, something is actually happening. That was at 352. And then that the highest velocities were recorded a little bit after 4:07 a.m. The reason for that lag is that the seismic station was located pretty far to the east in Romero Creek, and so it took a little while for the flow to actually come down Romero Creek and then go by the seismic station. But we need to consider that actually occurred after the gas line explosion, and the security camera footage is when we start seeing the increase in the seismic signal. So getting back to the point of early warning and avoiding the hazard, we want to take timely action to reduce disaster risks in advance. So looking at our data, based on the rainfall, we exceeded the threshold and had less than 7 minutes of lead time. Looking at flow detection and the seismic data, there was less than 4 minutes of lead time. So what can you do with 7 minutes of lead time? Now keep in mind, this isn't a bright sunny day in June. This is 3:40 in the morning. It's raining probably harder than you've ever seen in your entire life. You're tired, it's chaotic, you don't know what's going to happen. You don't know you have 7 minutes either. That's one of the dangers. So what realistically can you do with 7 minutes of lead time? Well, there's 3 basic options. You can stay in your home, you can go to the second floor or the roof, or you can seek higher ground. And that's about it. You don't have time to get really too far away. There's nothing you can do to protect your home at that point. So there's three options, and you don't have much time to do it, and it's a chaotic situation given it's dark, you're tired, and it's raining. So stay in your home. That's one of the options. Now in Montecito, that may work out quite well for you because the construction quality is pretty high in Montecito. There's this nice stone construction. The home itself was situated kind of outside of the main part of the channel, so you weren't in the highest velocity area. The caliber of the material wasn't quite as big. So chances are pretty good that this person, had they stayed in the home, would have weathered the storm okay. But if we move over a little bit to the channel axis, we can see that depending on where you were in the home would probably influence the outcome for you. So there's I don't know if you can see it, but there's a big hole in the house here with the boulder that came through. We're looking upstream, so chances are pretty good that this one also made it through that home. So if you decided to stay on the right side of the house, chances are it wouldn't have worked out too well for you. So staying in your home here, in this case, might not have been a good idea. And then finally, sometimes the homes just weren't there anymore. This is an entryway. There's a foundation here that you can see. And that home is no longer, we have no idea where that material went. Downstream somewhere, it could be in the ocean. So staying in your home really would not have been a good option in this location. You can go to the second floor or the roof. Again, these people, their home must be good, well constructed. There's a nice second floor that you could go up to. Fortunately, the flow just stopped at the top of the first floor. It would have been pretty exciting to ride out the storm here. I guess you could have sat out in your nice balcony and taken a look at the rocks go by. But you would have survived this event had you been in that house and on the second floor. It would have been scary, but you would have done it. Some people don't have second floors, so getting up on the roof in this case would be the option. Now I don't know if this was a rescuer going into the hatch in the skylight to see if somebody was in the house or if somebody actually evacuated out through the skylight. But if you do have a first story or one-story house, you better hope you can get up on that roof. And in this case, again, these people would have made it, but it would have been quite an exciting ride. But not all the structures stayed intact. This home actually shifted about 20 feet from left to right, and part of the roof is gone. So had you been weathering up on the second floor or on the roof, you would have had some problems. You can seek higher ground. So pile the kids into the car, get the dogs and the cats in the car, and try to get up a little bit higher and get out of harm's way. All the pictures I'm showing are not associated with places where there were fatalities. But had somebody been in this car, it wouldn't have ended well for them. And then if you were sheltering in place in your home, it might have been a problem for you too, because all of a sudden you have a vehicle in your living room. So getting out and seeking higher ground has its own set of issues. One being that vehicles don't really do well in really fast-moving mud and rocks. Again, you're taking a bit of a gamble if you get in your car. These two cars did not start the event together, but they ended up together. So this one, you may have been okay. This one, clearly not so much. So getting out of your house into a car and seeking higher ground is certainly an option of last resort. It's not something you want to rely upon to get yourself out of harm's way. So what can you do? Really, the only thing you can do is just plan well in advance. Be aware of the hazard. Be aware of your specific degree of risk. Attend the public meetings. Pay attention to the Weather Service through their website and the news, the local news, and their Twitter feed. They're going to be telling you when there's storms coming, when there's a storm coming, when it's time to evacuate, and then the local emergency officials will be going door to door and letting you know the risk. Now, this isn't a perfect system. There will be false alarms. They're going to be conservative in issuing watches, warnings, and the evacuation orders, especially now after what happened in January. So they're going to be conservative, and the system is going to fail from time to time. On the flip side of that, there could be a summer convective thunderstorm that pops up that really wasn't forecasted. So you may only have 15 minutes from when the warning's issued to when the flow occurs. So it's not a perfect system, but relying solely upon monitoring flow, you can see how problematic that would be because of the very, very short lead times. So we really have to pay attention to weather forecasts and base much of our warning protocol off of the forecast itself. So going back to the very first slide, in case you're just waking up, we've learned that post-fire debris flows occur within minutes of intense rain and repeatedly after fire. Early warning systems are much more than just detection of flow or intense rainfall. If you're measuring flow or rainfall in a watershed above you that's susceptible, it's likely too late to take any meaningful action. And then finally, the only 100% effective form of risk mitigation for the public is avoidance of the event itself. So if you want more information, we've gotten hit enough through Google that you can just Google post-fire debris flow, and it'll take you right to the USGS landslide hazards page that deals specifically with these hazards. And before we go into questions, I just want to acknowledge the efforts of the USGS Post-Fire Debris Flow Project Chief, Jason Keene, here on the left, getting dirty in Santa Barbara a few years ago, and Mark Jackson, the Chief Meteorologist of the Weather Service in Los Angeles, who has been incredibly supportive and creative and done a really good job of establishing the warning system and then showing people how useful it can be and increasing the popularity and the recognition of need for such a system throughout the Western U.S. And of course, this type of work doesn't occur without a team of really hard workers researching the problem. We've got a good group both in the USGS and the Weather Service. And a small group, but very productive. So folks in the Landslide Hazards Program, as well as in the Los Angeles Weather Forecasting Office, who've been there since day one. So with that, I think we have maybe 10 minutes or so for questions. We'll open it up to you guys and see what questions you might have.
Thank you, Dennis. Those of you who come regularly know the drill. We would like you to use a microphone to ask your question because we do record and archive these talks. There is one microphone set up in the middle of the room here if you want to make your way to it. If you have difficulty doing that, just holler, wave at me, and I'll bring a microphone to you. So go ahead with our first question.
That was great. So many questions.
Thanks.
So were the warnings that were issued, or the warning watch, I'm not sure which is more severe, did they actually result in people getting out of the way of those flows in Montecito?
Yes, the specific number of people that heeded the warning itself, it's hard to know. The compliance with the evacuation order was pretty low, though. So an evacuation order went out the day beforehand, and I believe the compliance was somewhere around 20%. So not very high.
I have more unless anybody else.
That's a good point. So for the next storm, it was 80%. And then 2 storms later, it was back down to 20%. Yep.
Is it possible to understand if your house is located where a debris flow is going to run? Or are the channels quite unknown before an event occurs?
It's really tough to figure out where flow is going to go in the built environment. Things like culverts and bridges can clog up and deflect flow outside of that channel, or that channel may be undersized because of engineering relative to what maybe it would have been, or when you have all that debris and not just clear water flow, your channel may be undersized for all that debris. So at that point, once the flow leaves the channel itself, it's really difficult to say where that thing's going to go when you're built on an alluvial fan. So it can be deflected by retaining walls or houses down a street that's several streets away from the main axis of the channel itself. We are working on modeling this, so being able to develop a run-out and inundation model that we can route flow and see where it ends up. But the main way to learn about that is through, if you're at risk, would be to talk to the emergency management agency in the community, because they're working with the state teams and the federal teams that are going out and actually mapping areas of risk.
After a lot of fires, I read that they're going out and seeding areas. Does that do any good? Secondly, does the angle of the hillside make a big difference? And then the soil composition, how does that affect the...
Right, sure. So the first question on seeding, I'm not a mitigation specialist, but I think that it can be effective in places where the slopes aren't incredibly steep. I think there's an upper limit to the gradient at which you can successfully seed a hill slope. I'm not quite sure what that limit really is, though. In terms of the actual steepness that matters, we found that slopes greater than 23 degrees are where we start really seeing debris flow hazards increase rapidly. We see that in both the historical database of debris flow, so we go and see where there was a debris flow in the past and measure how steep the watershed was, and we see that number break out in that database. And the folks at Caltech have also done some experimental work in a laboratory flume that shows the 23-degree angle of channel material. It becomes much easier to move all of those particles above that critical slope threshold. And then the third question, type of soil. That's a really good question. There's so much variability in soil properties just from 1 meter to the next. That it's hard to say as a general rule of thumb what could really contribute to enhanced hazard. One of the things we look at is sort of the erodibility of that soil, how easily it's eroded. There's a couple different ways of measuring that in the field, and there's a spatial database that we use that characterizes that at a fairly coarse scale. But soils that are more cohesive, that the organic matter survives the fire itself, are going to do better than the more mineral soils that we see in a lot of the western U.S.
I'm curious to know more about the production of a debris flow that suddenly has a whole bunch of material entrained in it. In the video you showed, there was a period where it was definitely flowing and it was muddy and stuff, but suddenly it just picked up this huge amount of debris that was carried. And can you say anything more about the physics of why suddenly there would be apparently land failure in the channel that would suddenly, offer a lot more load to being trained?
Yeah, sure. I think that there's several hypotheses that are out there now. And we don't have, it's really hard to test, so we don't have a clear explanation. But some of the things that have been put forth is that there's actually small failures of the channel bed itself. So underneath the flow, that the channel will reach some critical phase where all of that material will fail en masse. That's one possibility. You have bank failures, so the stream bank itself may collapse as a whole unit. And then the physics of the debris flow itself will actually push the coarser material to the front, and so there will be a segregation of material within the sort of longitudinal profile, just the natural physics of the flow itself. And so when you have those big boulders, it kind of makes a dam from which things kind of pile up behind it. So it may be, you may have that initial boulder dam roll through, and that'll be your first surge. But then another one will come through a little bit later, and so that's moving a little bit slower, and so the surges will kind of separate themselves out just based upon the properties of the material within the flow.
Okay, thanks.
I see some, okay, we'll have one last question here from Noel.
I appreciate the geological significance, but doesn't a lot of this actually pertain significantly to essentially climate change?
That's the hot question. I think that there's quite. I think that given elevated drought conditions in the western U.S., the fires are certainly more likely. Higher temperatures, drought, less rainfall, total rainfall. Fires are more likely. The more fires you have, the more opportunities you have for an intense band of rain to impact a burn area. And there's plenty of steep places in the U.S. that are steep enough to make debris flows. There's some question as to the role of potential climate change and what that would have in terms of rainfall intensity. There's some studies out there that hypothesize that you can actually get a bit more intense rainfall under warmer conditions. It does things to sort of the atmospheric physics that allow more moisture in the air. But that's sort of outside my area of expertise, but I do know that there are studies that are out there. So if you have warmer and drier conditions, you have more fires and you have the potential for more intense rainfall, even if you have less rainfall overall.
This was a combination of fire and rain. Was the fire particularly notable on the scale of fires that we have around here?
At the time, it was the largest in the state of California's recorded history. It's since been superseded by the ranch complex in Mendocino County this year. But at the time, it was the biggest.
No, but that measure of fire isn't what I'm after, because the only thing that I'm concerned about is the watershed area.
Right. So in terms of the intensity or the severity of the fire and the effects that it had on the soils and vegetation, it was a severe fire. The winds were really, really high during it. So it burned hot and it burned pretty quickly, but it burned really hot. Chaparral burns really intensely, and that type of vegetation can, when you combust it, it can really alter the soil itself. But for that area, I mean, I wouldn't say it was intense and it was a severe fire, but Southern California gets quite a few intense, severe fires.
And the rain was 100-year rain or
50-year at the 15-minute intensity, 200-year at the 5-minute intensity. And I think it tapered off to, I want to say it was a 5-year storm when you look at the longer durations. It just didn't last that long.
So this is nothing unusual in some sense.
In some sense, the 200-year recurrence interval, I mean, there's a fairly low likelihood of that in any given year, but it does happen. And Montecito has demonstrated that it's susceptible to flash flooding and debris flow in the past, in the late 60s and again in the 90s.
If you drove along the alluvial fan down at the bottom, would you be thinking that this is, this is how it got here?
There's some pretty big piles of rocks that
Yeah.
are on that fan, even not associated with this last event. Yeah, as a geomorphologist, I would wonder how they got there.
Thank you.
Yeah.
I was just wondering what use insurance companies are making, or have they shown any interest in your data and reports?
Yeah, we've had a couple Freedom of Information Act requests. I don't know where those go, but where we compile all the data and communications and package it up so people can access it. There's a few lawsuits, but one of there's a lot of negatives associated with this event, but one of the positives is that we're now in open dialogue with FEMA regarding what is the official stance on post-fire debris flows and the National Flood Insurance Program. There's some confusion as to what's covered for when you have a landslide versus a flood, and then this kind of debris flow that sort of resides in between the two. We're working with FEMA and the Weather Services. The Weather Service is largely spearheading that effort to clarify that for homeowners in future events.
When you're out on the ground looking at historic debris flows, could you see any difference between what might be a post-fire flow and debris flow and those from other causes? Is there any characteristic that would let you say this is a post-fire flow that we're looking at?
I think just looking at the sedimentologic characteristics of the deposit itself, it would be pretty tough. Post-fire debris flows tend to be a bit more watery, especially in the recessional part of the flow. So there's a lot more fine sediment. But I think probably the main indicator would be the presence of lots of charcoal. And I know people do date that and then construct both a fire history and a debris flow history from radiocarbon dates in Pleistocene and early Holocene events. Yeah.
Somewhat dismaying to see the public's reaction to your communication. Is anybody studying how to get us to be more responsive? And I thought maybe they ought to show that video of the rocks coming down, because without seeing that, I don't think you understand what it's all about.
Right. The National Weather Service did contract with some social scientists out of the University of Alabama to do surveys of folks in Montecito, folks that got out of town and evacuated, folks that stayed and weathered the storm. And I think it's nothing earth-shattering in what they're finding, but I think sort of the take-home messages, and this is they're still working through the publication process on this, but they're saying people weren't aware that there was a problem. They weren't aware how severe it would be in a debris flow, and so I think you're absolutely right. It's the outreach leading up to, even before the fire, and just educating the public as to what debris flows look like, how destructive they are, is really important. And so there were 23 fatalities associated with Montecito, and that's 23 too many. But I think if this was a decade ago, that could have been an order of magnitude higher. In terms of the way that the emergency management officials were communicating the hazard and communicating the risk. And then the Weather Service with their warning products and how on point they were getting those out and being accurate in their forecast and recognizing the importance of short duration bursts of intensity. Those are things we didn't know 10 years ago. So I think we're on the right trajectory. And while it's a tragedy that we lost 23 lives, I really think it could have been worse if this was 10 years ago.
Dennis, I just got back from Colorado visiting my brother who lives up 9,000 feet by Colorado Springs. And we drove out and we looked at the Hayman fire from like 2002. So that's been 16 years since then. And what struck me was there was very little revegetation other than what people had gone in and planted. And I know that was a very intense fire. What were the changes in the soil that preclude revegetation owing to the, I mean, does it get porcelainized or
in the Hayman fire
Yeah.
in particular, it's weathered granite, so it's a really coarse soil texture. So it just doesn't hold moisture. Any moisture that falls kind of just goes on through. There's lots of pore spaces, lots of void space. So I think it's pretty hard for vegetation to sort of take back over. I think, again, and that was probably lodgepole pine or ponderosa pine.
Certainly both are in there, yeah.
Was the vegetation type. And that, when you get rid of those completely, those do take a while to replace themselves. So the Hayman that's a very long recovery. And I think that there's some factors in changing environmental conditions where you're seeing a transition from one vegetation type to another following fire. In Southern California, in a lot of places that were chaparral, the chaparral is just not coming back. It's transitioning more to grassy, shrubby type of environment that's not the full mix of things that make chaparral as we know it. So I think there's the environmental conditions that things are a little bit different now than they were before. And then, like I said, the soil properties in certain places. But that time scale of recovery can be anywhere from a year, and Santa Barbara typically recovers pretty quickly. But Hayman fire in Colorado could be decades before that comes back.
What was the survival rate on big trees?
I'm not too sure. There were lots of, looking back at we did an analysis looking at aerial photography from before the event and after the event, and there were lots of big trees that were no longer there afterwards. So I don't have a quantitative number for you, but just looking at the photos, there's not very good if you're a big tree in the channel.
Well, thank you very much. Those are all really good questions. I want to thank you for coming and thank Dennis for a really informative talk.
Thank you so much.
Maybe we can replay the video that some of you wanted to see again. Otherwise, if you need to leave, please do, and we'll see you again next month. Thank you very much.